Okay, section 12.3 has to do with phase changes and heating curves. So you're probably pretty familiar with the different phases of matter: solid, liquid, and gas. And there are transitions between those phases. So transition from a gas to a liquid is condensation. From a liquid to a gas is vaporization. Transition from a liquid to a solid is freezing, and from a solid to a liquid is called melting, and scientists will also often call that transition fusion. So fusion is when a solid melts to a liquid. Then maybe some less common transitions. A gas can go directly to a solid without becoming a liquid intermediately. That process is called deposition, and then a solid can also go directly to a gas. That is called sublimation. And so these are actually more common processes than you might realize. Carbon dioxide, when it is cooled down enough under ordinary atmospheric pressures, will form a solid, and we call that solid dry ice. And you take dry ice and warm it up, and it will sublimate directly to carbon dioxide gas without melting. And that's why we call it dry ice, because there's no liquid phase that you observe under ordinary atmospheric conditions. And then deposition also, if you have frost on your lawn or your car in the morning, that is because because gas water vapor has deposited onto the cold surfaces of the windshield or the grass leaves. The grass, what do you call those? Anyway, on the grass. So that is a deposition process. Now, each phase change is going to have an associated change in enthalpy. It takes energy to make these transitions between phases. So if we look at the delta H of fusion, this is the energy required to melt a solid to make it a liquid. In the case of water, then that is going to equal 6.01 kilojoules per mole. And then we can have a delta H of vaporization. That's how much energy is required to go from a liquid to a gas. And in the case of water, it's 40.7. And then we'll have a delta H of sublimation. So if you go from a gas directly to if you go from a solid directly to a gas. And this, it's perhaps not surprising, is going to be 46.7 kilojoules per mole, or in other words, the sum of the first two. And we've got a diagram here in your textbook that can show why that is, figure 12.15. If we consider the energy levels of the solid and the liquid and the vapor phase, and apply Hess's law, which we covered in Chem 1210, it's very clear that if you start from a solid and end as a vapor, the total change in energy should be the same whether you do it in one step or whether you do it in two, because enthalpy is a state function. And so figure 12.5 shows that. Now, also looking at this energy level diagram, we can think about the opposite phase transition, so condensation, going from a vapor to a liquid, Well, the delta H for that would just be the negative of delta H vaporization. Freezing would be the negative delta H of fusion, and deposition would be the negative delta H of sublimation. So if we wanted to calculate how much energy is needed to vaporize, let's say 10.0 grams of water. And we're going to want to be very careful here and make sure the water is already at the boiling temperature. So we don't need to heat up the water at all. We just need to make that transition from liquid to gas. So I'll say at 100 degrees Celsius, the boiling point for water. So how much energy is needed to vaporize 100 grams of water at 100 degrees Celsius? Well, we need that vaporization enthalpy. And then we also need to recognize this is a molar amount. And so we'll convert our 10 grams into moles. 10.00 grams of water. It's 18.011 grams is 1 mole. So let's do that calculation. Okay, so I've got my calculator up here. We'll do 10.00 divided by 18.011. And that looks like it's going to be 0.555. moles of water. And then this enthalpy of vaporization gives us kilojoules per mole. And so the equation that we would want to use is the total heat Q is equal to N, the number of moles times the enthalpy of vaporization. So this is going to be 0.555 moles times 40.7 kilojoules per mole. Again, we'll go to the calculator. .555 times 40.7, and I get 22.6 kilojoules. That is the total energy that would be required to vaporize 10 grams of water. And I want to kind of emphasize that this is different than another familiar heat equation, which is Q is equal to mc delta T. So this tells you the heat required to change the temperature of a substance, and it refers to its mass and its specific heat, which is usually given in joules per gram degree Celsius. Here we have the heat of transition change is equal to the number of moles times the enthalpy of that transition. And I also want to point out that table 12.3 will give enthalpy of vaporization and fusion and sublimation values on a per gram basis. And so sometimes it's easier to use those values instead of the molar values that I gave you in the lecture here. Use whichever is most convenient to you. They are consistent with each other, and it's just a matter of making sure you use, you're aware of what units you're supposed to be using together with which enthalpy values. Okay, so I want to show now what's called a heating curve. So in a heating curve, we see how the temperature of a substance will change as you add heat to it. That's pretty obvious as long as there are no phase changes. If I add energy to a substance, then its temperature will increase. But you'll notice on this curve there are a number of plateaus. So if we look here, starting at negative 20 degrees Celsius, if we add heat, then the temperature will increase, and that corresponds to super cold ice being warmed up to the melting point. 0 degrees Celsius is the melting point of water. And then as we continue to add heat to it, the temperature will actually remain constant. The heat that we add is not being used to change the temperature of the substance. Instead, it's causing the melting transformation. And so we start at ice, solid water, and then as we add heat, more and more of it melts until at this point it has completely melted. There's no more ice, it's all liquid water. And now as we add the heat, then the temperature will begin to climb until we reach the boiling point of liquid water at 100 degrees Celsius. And here we enter a new phase transition, vaporization from liquid to water vapor. And you may remember that enthalpy of vaporization was a very large number, 40.7 kilojoules per mole, and so it's going to take an awful lot of energy to complete that phase transition. Eventually it will be all water vapor, no more liquid water left, and then the heat that we add from then on will increase the temperature of the water vapor. And I think this is actually a little bit surprising when you first look at it, but really we understand this really well, especially in terms of the liquid to vapor phase. If you put a pot of water on the stove, I think you've had the experience of noticing that that water gets warmer and warmer and warmer and warmer until it reaches the boiling point, and that boiling pins the temperature to the boiling point, 100 degrees Celsius, and there's nothing you can do to add more heat and make the temperature go up. Instead, the heat you add goes to phase transition. You can construct a similar curve where you start maybe with water vapor and you cool it down into a liquid and then down to the freezing point, and you freeze it and do this whole process in reverse. At each stage here, if you wanted to quantify this, if you wanted to use actual values for heat and delta T, then you would have to use a different equation at each point. So for the warming of the solid, you would use Q equals mc delta T, where C is the specific heat of solid water. And then for the melting, you'd use Q is equal to N delta H of fusion if you're using a molar amount, or M delta H of fusion if you're using a mass. And then warming the water, you'd use Q equals mc delta T, but this time you'd use the specific heat for liquid water, which is about twice the specific heat for solid and vapor. And so the specific heat depends on the phase, and once you reach the boiling point again, you'd use Q is equal to N delta H of vaporization, or M times delta H of vaporization. And then finally for this last phase, Q would again equal mc delta T, only this time you'd use the specific heat for water vapor. So anyway, we have a quiz that's going to sort of analyze one of these heating curves in exhaustive detail, so I won't belabor the point right now. Just make sure you watch the solution video for that quiz.